Welcome. Yeah, so let's get serious, but let's not be corny, so never say that again. Okay, as usual, thank you, Lord Jesus Christ, for all your blessings and for another day of fun with math videos. Now, recently I came across a bunch of really fun, challenging questions on the convergence and divergence of infinite series, and so I thought, we should start a playlist called the Fun Challenging Infinite Series playlist. And so it will have at least 10 problems in it, the first of which is this, super fun. Okay, now, part of what makes infinite series, and therefore the question of do they converge or diverge, challenging, part of what makes it challenging is that there are way too many tests, right? And to kind of help you, although I've said this in other videos on infinite series, the order in which you should go through them is ask yourself, okay, is this the infinite geometric? And even before that, maybe use a divergence test. But remember, the divergence test tells you if you diverge. It doesn't tell you if you converge, right? But yeah, you've got those two, divergence test and infinite geometric. And then after that, you ask, is it the harmonic or alternating harmonic? But that's two very specific series. And so you can't really do much with that. In other words, that's not a test, the harmonic and alternating harmonic. But they are very useful, usually, for comparison purposes, especially the harmonic series. Hint, hint. Okay, anyway, you go through those two, right? And thereafter, it's in the order integral test and p-series, because remember, p-series is a consequence of the integral test. And then after that, what do you have? Limit comparison and direct comparison. And those two are very, very closely associated with one another. In fact, I have proofs of the limit comparison and direct comparison. You can see that the proofs are very similar to one another. Yeah, so you've got those two. And then you've got the alternating series test. It's a lot of them, right? And then the ratio test, which is kind of like the shotgun, because you can take care of a lot of infinite series with the ratio test, and you can even use it to find intervals of convergence, blah blah blah, right? Okay, so you've got that. And then after that, you've got what? The nth root test. And I don't think I left out any. Is the series telescoping or not, but that's very specific, and we'll have examples on that. So this video, among other things, is to kind of pose some challenging infinite series and ask the question of convergence and divergence, but it's also to help you figure out which test to use when, right? Okay, so let's get on with it. Now, sometimes what makes an infinite series and the question of convergence difficult is that the a sub n that you're given, that's, if we cast this as being n equals 1 to infinity, a sub n, obviously a sub n here is sine of 1 over n. Yeah, so sometimes what makes it challenging is that the a sub n has very little, right? Here, for example, it's not a quotient, right? So those kind of things make it a little bit tricky. So, well, that's why it belongs in this video series, right? Anyway, let's go to this visual to see how we could deal with this. In other words, how to pick a nice second series to compare to this one, right? If you look here, and in fact, one of you noticed recently, one online student noticed that sine x is approximately equal to x on some limit question I was doing. Anyway, this should be true. This should be very clear. One, because of this visual, because if you look at the sine function, which I have in black here, and then the line y equals x, so you consider y equals sine x and y equals x, then near 0, they're very, very similar to one another. And you can use Desmos, a great online graphing calculator or graphing tool, to graph both of them on the same axes, and you'll see that y equals x is always on top of the sine function. But here they're very close to one another, right? Okay, cool. Well, what can we take away from this? Well, an addendum to that is you could also gather that sine x is approximately equal to x if you know Maclaurin series. Anyway, what we gather from this is, since, as I said, x is on top of sine x, I can say this, right? I could put a less or equal to right there, right? Okay, cool. And then if I choose x to be 1 over n, look at what this inequality turns into. I'd get sine of 1 over n is less or equal to 1 over n. Great. Okay, so this gives me my bn that I should compare to my an, my bn series, I should be specific. And so our bn series, I'm going to write over here, is going to be n equals 1 to infinity, and then I'll just write bn here, but it is equal to n equals 1 to infinity of 1 over n, because, well, we're drawing from this, right? So Bn is 1 over n, and so the Bn series is this. Is it familiar? It better be. This is the very famous harmonic series, right? This is the harmonic series, and it famously diverges, right? So this diverges because it's the harmonic series, right? Okay, we know diverges. Cool. So then what could we do? Well, we could do the direct comparison or the limit comparison. Now, since our second series Bn diverges, for divergence, if we choose the direct comparison test, I'll call it a direct comparison test, DCT, then what we require is that we find a series B sub n that is less or equal to our A sub n. That's a problem because our B sub n is bigger than our A sub n, right? Bigger or equal to. It's not lesser. So that rules out the direct comparison test, because for divergence in the direct comparison test, our second series that we come up with, i.e. that, has to be lesser than our original series, and that's not the case here. But the limit comparison test will come to the rescue. So limit comparison test, right? Okay, how do we use the limit comparison test here? Remember what it said. What it said is, if you take the limit as n goes to infinity of A sub n over B sub n, and you find that it's equal to some constant c, and you find that c is positive, that is 0 is less than c, and c is also finite, so c is less than infinity, then it says that the series made of an and bn, they either both converge or they both diverge. So in this specific problem, the limit comparison test will have us write the following, which is, it'll have us write the limit as n goes to infinity of A sub n. A sub n is sine 1 over n. You'll see that this is really exciting. Over B sub n, which is 1 over n. Well, we have to figure out what it is, and if it is some constant c that is positive and less than infinity, then since our series made of 1 over n diverges that, we will conclude that our series made of A sub n, this fella, also diverges. Yeah? Okay, cool. Well, we have to deal with this limit, right? Does it look familiar? It better look familiar, right? Doesn't it look like that very famous limit? We don't need this stuff now, so I'll write over here. But doesn't it look like that very famous limit that we have, like, you know, a few videos that connect to it and one dedicated to it? And that famous limit I'm talking about is the limit as theta goes to 0 of sine theta over theta, right? We prove this using the squeeze theorem in a video dedicated to it, and this is equal to 1, right? Okay, cool. So this looks very much like it. It looks like what we should do is like let theta equal 1 over n. Okay, if theta is equal to 1 over n, this quotient is going to read sine theta over theta, and notice that the limit here says n goes to infinity, but as n goes to infinity, theta goes to 1 over infinity or 0. So n goes to infinity means the theta goes to 0. I'm saying for the replacement of the limit, we could write limit as theta goes to 0, because as I just said, as n goes to infinity, theta goes to 0. So using this translation with the substitution, theta be 1 over n, this limit becomes this, which we famously know is equal to 1, and clearly 1 is positive, so it's greater than 0, and less than infinity, so either both series converge or both series diverge is what we said. Well, since we knew the harmonic series diverges, this series also diverges. Diverges. Okay, that sounded cruel. All right.